Okay, I wanted to continue showing you some of the features in multisim and looking at some of the other measurement instruments that you have available. And like I mentioned this before, even if you haven't taken AC, I think if you look at it from the mathematical point of view, at least the description of sinusoidals, is easier to understand, and then just look at how some of that can be used to make measurements on this type of signals. So don't worry much about not necessarily knowing the theory behind AC, because we're looking at this more from the practical point of view, okay? For those of you that have taken AC, of course, this will make a lot more sense. But anyhow, I'm assuming, again, based on the survey I sent early in the semester, that most of you have already taken DC. So that I will take it as you understanding most of it. But in any case, last time we were talking about AC signal just being basically mathematically expressed like any one of these two functions here, like a voltage or a current, which is described by an amplitude, a phase angle, and a frequency. And just to recap, the amplitude, of course, is however high or low the signal will go. That's what determines the amplitude. The frequency will be how often it's going to change or not change, depending on the frequency. The higher the frequency, the more often the signal is going to change, and the slower the frequency, the less often the signal is going to change. And the phase angle, of course, determines how much the signal is going to shift on either direction along the x-axis, because the x-axis, when looking at this type of signals, is of course the time signal. So if you understand this, again, just from the mathematical point of view, then, it's a lot easier than to look at the information that we'll see based on the instrumentation. In any case, we looked at the oscilloscope last time also. And just to remind you, when you look at a scope, you're going to see information like this on the screen, which shows you the voltage information about one or more signals, where again, the y-axis shows the voltage information and the x-axis shows the time information, okay? And if you look on the right-hand side, I have put two different pictures of, what an oscilloscope screen may look like. With a little more detail. Again, the y-axis represents volts, and the x-axis represents time. And as you see, there are little squares inside inside the big rectangle here in the screen, and each of those squares represents a division. So that means that if depending on how you set up your scope to read, you can set up, for example, to have 1 volt per division. Okay, so if you, in this instance, or in this instance at the bottom here, if you look at the different squares, if I have set up the scope to be 1 volt per division, excuse me, then the maximum that I can, excuse me, the maximum that I'll be able to see will be 1, 2, 3, 4, 5, 6, 7, 8 volts peak to peak. Okay. In other words, because each division is set up to 1 volt, the maximum that I'll be able to measure on that setup will be 8 volts. If I change it, of course, if I change it to 2 volts, then I'll be able to see more and so forth. So that's something you can adjust, right? How much each of those squares is worth on the x-axis and on the y-axis. In the same way, if I change the setup for the x-axis per division, let's say I have 1 second per division. If I look at 1 second per division, then the maximum that I will see at any given point will be 1, 2, 3, 4, 5, 10 seconds of the signal, right? If I have set up the x-axis or the time axis as 1 second per division, then I will be able to see 10 seconds of the signal at a time. If I want to see more of the signal, then I can make these squares worth less. And if I want to see more, I can increase, or if I want to zoom in, for example, I can increase how much I'm dedicating to each of the squares. In any case, that's the same information you see here, right? I've said that this one has a little more detail because also inside the squares here, you see little ticks, right? And that gives you a little more detail on what you can see on the scope. So for example, again, if you go back to the idea that each vertical position is set up to 1 volt, then each of those ticks will be 1/5 of a volt. Right? If, again, if I set up this with the scope to be 1 volt per division, then each of those little ticks will be 1/5 of a volt, and so forth. Same thing goes for the time information. So that gives you a little more detail on what you can see. So with that said, then I'd like to go into multisim now. And let me just make sure here that you still see this. Just a minute. All right, so again, this is my multisim area. So what I'm going to do is I'm going to bring just a simple AC signal and then take some measurements with it. So simply going to go here and pick on an AC voltage. And of course, I want to get a ground for that. And so I'm going to get a ground signal and I'm going to ground it. Okay. And this particular signal that became by default is a 1 volt peak signal at 1 kilohertz. 1 volt peak means that the amplitude is going to go up 1 volt and is going to go down 1 volt. Okay, that's all that means. And the 1 kilohertz means how fast it's gonna change because it's a periodic signal. So I'm gonna use, last time I used a simple scope, right? To the default scope, remember, to measure that signal very simply, right? Let me just do that again. Okay. And if I do that, sorry, let me ground this. I'm gonna need another ground. So very simply, if I double click on this and I run it, I will see the signal here. And if I want to change, again, see how I can change the volts per division and the time per division, the scale, right? So if I want to see a little more of it, I can increase or decrease depending on what I want to see, right? So this here, and this is the virtual scope. So I'll show you in a minute what the actual scope looks like, the real scope. But in this virtual scope, I can manipulate how much I see of the signal by changing the scales, either on the vertical scale or the horizontal scale, okay? So we did this last time, so let me just close that and then show you now a different scope, which has a lot more detail. Okay, so now I'm going to bring and by the way, you notice here that you have other kinds of scopes. You have the Agilent scope, which looks something like this. It's a 2-channel scope, is a little older one. This is more of the type you have in the lab. And these are digital scopes. There's another one that is a little more advanced and a little more sophisticated. This one here is also very nice because this one, let me get rid of the other one. This one here has 4 channels, meaning that you can see up to 4 signals at one particular time, at any point in time. And not only that, but it's colors. So the signals are also determined by the color you see. So yellow will be channel 1, blue will be channel 2, pink is channel 3, and green is channel 4. So you always know which signal you're looking at by the color of the channel. So there's a 4 channel here, and there's a whole lot of other features in here. Okay, this is a more expensive scope, but it's exactly how the real one looks and how the real one operates. It is the real thing. So I wanted to show you that just so you can be familiar with this, especially when you go into a lab environment, which you will be seeing something like this. Okay, so I'm going to measure the same signal again and move this around. So I'm going to measure the voltage at the input here, simply, okay? And I'm just going to run it. Okay, first of all, you have to turn this on, right? If I run the simulation, it's not going to do anything because this device is not on yet, okay? Not like the virtual devices. The virtual devices, if you notice, you don't have to turn anything on. But these other devices, which are more like the real thing, you do have to turn them on. So that's a little different, right? So let me turn this on by just clicking on the power, and now you know that it's on. And I'm going to select this as channel 1 because I'm using channel 1. As you can see here, the channels are numbered right from 1 through 4 in the same order that you see them here. And then I'm just simply going to run the simulation. As you can see, I start seeing the signal. Again, I can control now. This is more like the actual physical device, because now I can control by moving the knob. I can control how much more or less I see of the signal, right? Because I'm adjusting, by doing this, I'm adjusting the number of divisions or the number of volts rather per division. And you can see that information here on the top, on the bottom left here, right? See how I can change, by changing that, I'm changing the volts per division. So this means that each of those squares is one, each of those vertical positions is 1 volt. If I keep changing it, you see that now it is 200 millivolts, 50 millivolts, keep going the other direction, is 5 volts, 2 volts, right? So again, see how that allows me to look at the information I want. So let me bring it to a little, maybe like that, 500 millivolts per division. And the way I control the x-axis information is by using this knob. The timing information controls all of the channels, okay? So I can control the individual volts per division with each of these knobs for each of the channels, but the timing information affects all of them at the same time. So again, if I move this knob either left or right, see, I'm changing the divisions, the number of seconds per division on the x-axis, of course. And now, as you can see here, that's the information it's telling me that each of these divisions here is now it's worth 500 microseconds. So if I keep just doing one more, you can see a little bit of information. I'm going to stop it so you can see a little more of the signal. Okay. So now you can see, right? It shows me 1 cycle. And as you can see, it says that each of these vertical settings is 500 millivolts. So that means that the 2 of them here is 1 volt. So that's what the signal is 1 volt peak. So it goes 1 volt up, 1 volt down, see? And it's also telling me that I have 1, 2, 3, 4, 5 divisions in 1 cycle. See, 5 divisions for 1 cycle. So if I multiply the number of divisions, which is 5, by how much each division is worth, then I have 1,000, 1,000 microseconds. And 1,000 microseconds is the period, right? So if I take the inverse of the period, I get 1 kilohertz. Okay? So that's how you can tell, you know, what you have on the screen here, right? And again, if you look at the total number of divisions on the y-axis is 1, 2, 3, 4. So if I multiply 4 times 500 millivolts, you have 2 volts peak to peak, right? Now this particular model of oscilloscope has all the features that we're not going to get into it because it's not the purpose here, but it has all the features that it'll show you on the screen, you know, the actual information you're looking at in terms of frequency, period, and voltage peak to peak. So you don't have to really compute it or not compute it, but calculate it from the screen. But it's always important that you know how to do it on the screen. At least you have a feel of if what you're looking at that you know, really is making sense. Okay, so just to show you, I'm going to stop it and I'm going to add a couple of devices here. I'm going to add a resistor and I'm going to add a capacitor just to let me get rid of this connection first. Sorry about that. Let me get rid of this connection. And I'm going to add a resistor in series of my input. And I'm going to also add a capacitor, so that capacitor will give me some filtering effect. So I'll see the output, I'll see something a little different. And we did some of this last time, but without using this kind of scope. It won't make a difference on what you see, it's just that this scope is a little more sophisticated. I'm going to use again a 1 microfarad capacitor, and I'm going to hook that up to the output. Like so. Like so. And I'm going to use the channel 1 to look at my input signal. And I'm going to use channel 2 to look at my output signal. Right. So now I'm connected. I'm not using this. I'm not using this ground here, so I'm going to get rid of it. So now I have the two channels connected, one to the input and one to the output, right? Channel 1 again is still yellow one. Channel 2 will be blue, and I'm going to run it. But you'll notice one thing, right? When I run it, and I'm going to just click on, because I stopped it before, I'm going to run it again using this button here. Notice here that I'll only see the input again, right? So the reason for that is because I haven't really turned on channel 2. To turn on each channel, I just have to press this button here. So I'm going to turn on channel 2. In fact, if I want to turn off channel 1, I press this button. I don't see anything, right? I don't see any of the channels. So I'm going to turn on channel 1, and I'm also going to turn on channel 2. And now you see channel 2, see, in blue. And so I'm looking at the output across this capacitor. So obviously the output is attenuated because of the effect of the capacitor, which again, at this point is not critical that you understand that, but just understand that the output is being attenuated, but I'm not really seeing it very well on this scope. So what I can do is adjust the divisions for the channel 2 information. So if I'll do that, you can see that, right? And now I can see a well-defined output, right? But what I notice now is that, if I stop it again, is that obviously channel 1 didn't change. It's still 2 volts peak to peak, right? It's my input signal, still 1 kilohertz. But the output did change. Now the output is less than that, right? Because you notice now that the channel 2 is set up to 100 millivolts per division. And so if you look at this from top to bottom, I have about 1.5 up and 1.5 down, right? So I have a total about close to 3 divisions, right? So 3 divisions means that I have approximately 300 millivolts at the output. See? So this output signal is approximately 300 millivolts per division. The other thing you notice is that the frequency is not going to change because the input frequency, the output frequency will be the same in this case. But what you notice here is what we talked about phase shift, meaning that the output signal is shifted towards the right, see, with respect to the input signal. And that's what represents an output shift. So again, see how powerful this is because it shows you that information on the screen right away, okay? All right, now I'm gonna show you another instrument that we can use. I'm gonna stop this. And what I'm gonna show you is there's also an instrument that we can use to generate this kind of signals, the input signals. It's called a function generator. And the function generator is located somewhere in here. There we go. This function generator, okay, is used for input signals, right? So this scope is going to measure something like, you know, like my just a minute. It's going to measure either voltage, right, information that I want for whatever signal I'm looking at. But this device here called a function generator is used to generate all sorts of signals, not just voltage, not just sinusoidals like this one, but other kinds of signals. And I'll show you that in a minute. So what you see here, and this is the one you're going to see also in the lab. This is the actual one that you're going to see. It looks exactly like this. And what you can see here is different things. Starting from this button here, you can see the signal that you can generate. You can generate a sinusoidal, a square wave, what's called a sawtooth wave, a ramp function, right? You can generate all those kind of signals. You can either do some other more sophisticated things that you don't even get into the lab at this point, but some of the things that you can change is the frequency, the amplitude, okay, of the signal that you want. So just like this signal that I picked from the devices here can generate, you know, a voltage at a particular frequency, and I can change it by double clicking, right? I can change the voltage that I want. Maybe if I want 5 volts peak to peak, and I want to change the frequency to 5 kilohertz, right? This will change the virtual supply to that signal. Well, I can do the same thing with this device, right? So what I'm going to do is I'm going to replace the virtual signal by the actual device here, okay? And so what you notice is that it has an output port, right? So I'm going to grab that output port to here, okay? And I'm going to, again, to use these instruments, you have to turn them on. So I have to physically push the button here to turn that on, right? So by default, it's giving me and you can tell what kind of signal you have by this little symbol here. So by default, it's giving me 100 millivolt peak-to-peak signal, sinusoidal signal. If I select this, you can see here, it's going to turn into a rectangular signal, here into a triangular, and here into a ramp signal, see? So this little symbol tells you what kind of output you're getting from here. Let me go back to the sinusoid, okay? And what I want to do is I want to change the amplitude and the frequency that I want, right? So I'm going to select, you can see here the button, the second one from the left says amplitude. So I'm going to select amplitude, and there's 2 ways I can select the amplitude. I can use this big knob and start changing it, you know, and this will give you a little more precision, but it's hard to, you know, go to the point that you want that way. Another way that I can do this is I select the digit by using this buttons here. So I'm going to move to the left. Oops, one more. And look at the 5. Right now, the button or the selection is at 5. So I'm going to increase it. I'm going to increase it by using this button here, right? So I'm going to go say 1, and now I have 1 volt peak to peak, right? So let me go to 2 volts peak to peak, and I don't want that 8 there. I don't want exactly a 2 volt peak to peak. So I'm going to move the cursor again by using these buttons, and now I'm going to go to the right. So I want a 0 here, and this one I want to make it a 0. So I can then use this knob to bring it down to 0, and now I have a 2 volt peak to peak signal of an amplitude I selected. And the next thing I'm going to choose is the frequency, right? So the frequency by default is 1 hertz. And let's say I want to change it to 5, it's 1 kilohertz. And let's say I want to change it to 5 kilohertz. So again, I'm going to use this buttons here to move. And now I'm at the first digit. I'm going to go up. I can also use the knob at this point, see, right? And I'm going to select 5. So now this is set up for a, look at the amplitude, a 2 volt peak to peak signal at a frequency of 5 kilohertz, and it's a sinusoid, okay? So that's going to be my input. So let's look at the input on channel 1. And the output again will be channel 2. So I'm going to turn that on now. Okay, and I'm going to run it. And as you can see now, my input, I'm gonna turn off the output so we can look at the detail for now. But the input is this, right? A 5 kilohertz signal at an amplitude of 2 volts peak to peak. And if you look at the divisions again, I'm going to expand it to see a little more. And I'm going to do this, so that's better. Maybe one more. Yeah, there you go. So now if you look at the number of divisions, I have 1, 2, 3, 4 divisions times 500 millivolts gives me 2 volts peak to peak, right? Which is exactly what I have set up this to give me, right? And if I look at the output now, I can select this, and again, you can see the output now. And if you want to see a little more of the output, I can use this knob. Oop, there we go. Okay. And you see the same information as before, but this one is a little more sophisticated, and this one can select more precise signals. Also, if I want to change this to a square wave, I can just simply select square wave. And now something different happened because this guy, the effect of a of a of a capacitor is to integrate the signal in real time. And that's why you see the integration of the square wave here. Anyhow, if I change this to a sawtooth, you still see that. And if you change it to a ramp, you see that as the output, right? But I can easily change that. What else can you do? Let's see. Yeah, frequency, amplitude. Just say if you're curious, also you can generate all the kinds of signals like an amplitude modulated signal, FM modulated signal. So if I wanna do that, I can and see that is selected by the top information here in blue. So if I select Shift and change it to AM, now you can see how the signal is being changed because it's being modulated. Okay, and that's what modulation does. That's see. Now you see it more like a real AM signal looks like. Okay, so you can use this device again for all of that. Okay, all right. Let me just pause for a minute. The other instrument I wanted to show you is the multimeter, but this one is a digital multimeter. Is the actual device. And this is also the same one you're going to use at the lab, if not very similar. And I show you how to use that. So let me get rid of the scope here. Let me get rid of the function generator. And I'll show you how to use this multimeter. It does the same thing as the regular meter that we use, although this one is very simple, right? This one, of course, is used to measure voltage, current, and resistance. With this one, you do the same thing, but is a lot more sophisticated. And you can do other things also with it. So let me get rid of the scope here and the function generator and just look at the, and I'm going to use just a simple resistive circuit, right? So let me just do a base here, and I'm going to, I guess, keep it at 1. That's okay. And I'm going to bring a just a simple DC signal, and I'm going to make that a 12 volts, okay. And I'm going to connect these two together like so. Okay. And now I simply want to make some measurements here. Okay. So the nice thing also here is that you'll see the measurements live, right? As you know, as they're happening. So and okay, you here, just change that to look a little nicer. There we go. All right, so I want to measure, let's say I want to measure, let me add another resistance so that I can be a little more challenging here. I'm going to put another one here. And let me change this one. I guess it's okay. The values are fine. So let's say I want to measure, and I think we did something similar before using this instrument, right? To measure voltage and current. And we also use the probes to measure the voltage and the current. But now I want you to understand how to use this device to measure voltage and current, okay? Again, just like the other ones, if I want to use it, I have to turn it on. I have to turn the power on here, okay? And you notice here, what you notice is that we have ways that we can measure, right? Here you have DC voltage, right, in this main button. And you can see here, let's look at this button first. It says DC voltage here, and on the top it says DC current. This one says AC voltage, AC current, and this one measures resistance at different sizes of resistance that you want to measure, depending also on the power of the resistor. There's all other things here that again, we're not going to use. You may be using some of those when you take the electronics lab, but they're not in the AC/DC part of it. But in any case, it's easy if you understand how to use these buttons or the features. You'll find it easier to understand the rest. So so what I want to do is I want to measure the voltage across the resistance. First of all, let's just measure a simple resistance, right? I'm going to again just put the value here of this resistance, and I'm simply going to select what I want to measure here. And if you can see here, you see what the connections are for measuring resistance or voltage. And these two you use to measure current, okay? So you use this at the bottom to measure current, and this at the top to measure either voltage or resistance. So I'm going to simply use this and plug it in here, and use this one and plug it in here, connect it in here, right? So as you can see, I made the connections, right? So I'm going to measure resistance. I'm going to press the resistance here, right? The resistance button. And if I click on go or run, then I'm measuring the resistance, as you can see, right? To see more of this, we can I can replace this one by a variable resistance. So let me do that here. So I'm going to go to variable resistor. I'm going to keep it, let's make it a 10 kilo ohm resistance. Okay. And I'm going to move this out of the way. And just to see again how this works, I'm going to again run it. And as it is right now is a 50%, right? The setting is a 50%. So it's going to measure half of 10 kilo ohm, right? So at 100%, it's going to be close to 10 kilo ohms, right? Which is it should be. And if I make it like a 10%, it's going to be 1 kilo ohm, right? Again, you can see, you know, different settings here of the variable resistor gives me different resistance, right? You see the idea now. Okay. So that's how simply can be used to measure resistances, right? And you can see here it's telling you what connections are you making because it kind of tells you by this going white here. All right, so let me stop this and I'm going to get rid of this resistor and I'm going to use the device to measure. I want to measure the current through R3 and I want to measure the I'm going to use two of them, something that you normally don't have in the lab, at least you don't have that available. But just to show you again how to use it, how to set it up. I'm going to turn this one on too, and I'm going to use the top one to measure voltage. I'm going to use the bottom one to measure current. Okay, so if I want to use the top one to measure voltage, I'm going to set it up to DC volts. All right. And if I want to use the bottom one to measure current, I'm going to set it up to DC amps or DCI. But to set it up to DCI, see how the DCI is at the top of the button here? I'm going to have to select Shift. If I click Shift, DCI now is ready to measure amps DC. Okay. Okay. So this bottom one now is set up for current measurement. This one is set up for voltage measurement. Again, use the Shift DC button here to select the top, right? If you're going to go back, I select Shift and click on this one again, and it goes back to whatever I want. See, just click on it. But if I press Shift, go back to AC. I mean amps DC. Any case. And then the idea is the same again, right? If I want to measure voltage, so I want to measure voltage with this one, so I'm going to go from here. So I want to measure the voltage across these resistors, resistor R1. Oops, I made that. This is nice because it tells you this is wrong, right? You don't want to. You want to be between the red and the black. So actually, I need this one here. Okay, so this is now set up to measure voltage, right? Now I want to measure the current through this resistance here, right? So remember, to measure current, you have to disconnect the device and put the meter in series. So to measure current now, I'm going to use this bottom one, okay? The bottom is used to measure current, okay? So again, I'm going to select this one to go through the resistance side and this one here to go to the other side. Okay, and now I'm ready to start measuring. I noticed that I was using this top one to look at the current, but that wasn't the setup that I had originally. I was meaning to look at at this one to measure the current, right? So let me wire that, right? So like I said before, I'm using this one to measure the voltage, and I already hooked it up to measure the voltage across R1. And I'm going to set up this one to measure the current through our the 1 kilo ohm resistance. So again, I have to use these two button connections to have the current that I want. So I'm going to hook up my resistance here, and I'm going to hook up the other side of the resistance to here. And now, as you can see, these two are connected in series with this resistor, and these two connections are in parallel with this connection here, right? And so I'm going to run it now, right? So now this is set up to measure voltage, this is set up to measure current, and I'm simply going to run it. And I have 8 volts across here, and I have a current of 4 milliamps across here, or through here, rather. Okay. And so, as you can see, how easy it is to make those measurements, right? As you can see, this is actually correct, right? Because if you do voltage division here, right, then you can see that you will get 8 volts across here, and so that's 4 volts across these two, right? In any case, that's how simply it is to make measurements. I'm not going to show you how to do measurements in AC because that requires an explanation that we, some of you that are not taking AC may not be able to grasp at this point, but you will, make the connections the same, except that you will select AC for voltage or AC current. And the value that we'll see will be a little different because of other items that come into place with AC. But the connections and the way you use the instruments and how you make the connections are the same. Okay? So I hope that was useful with the introduction of the scope, the function generator, and the multimeter that is more like the actual devices you'll see in the lab environment. The next topic I want to show you is how to use some of the integrated circuit devices like the operational amplifier. Again, if you take in DC, you should already have an idea of how an operational amplifier works. Okay, it's part of the DC curriculum, so hopefully you already seen that. But if you don't, I'm going to give you an overview, and I think the overview will be enough for you to at least grasp the idea of how the operational amplifier works. So no need to go into the theory if you haven't seen operational amplifiers, which I hope you have if you take NDC. But if you haven't, I'll give you just a brief overview, and you'll see that we basically interested in the result. What does it do? Okay, we won't be interested in knowing how does it do it. But an operational amplifier is an integrated device, an integrated circuit. And it basically has five connections, okay? 2 of the connections are the inputs. There's 2 inputs, 1 output, and 2 supplies. It needs power supplies to work, okay? That's the basic idea of an operational amplifier, that it needs power to work, to do what it's going to do. Now, the basic characteristics are that it has an infinite input impedance, it has 0 output impedance, and basically has a large gain. And those are the 3 things we're interested in for our purposes here, without going into a lot of detail. And knowing that, we'll see how easy it is to use it, okay? So what I'm showing you here is that based on these characteristics, right, we can apply very easy an analysis to this device. And without really even going into the details of the analysis, for those of you that have not seen operational amplifiers, what I'm interested in here is in showing you the results and then showing you in multisim how you can easily corroborate those results, okay? So anyhow, so when we hooked up an operational amplifier this way with a resistance in the feedback mode, right? Because it goes from input to output from the negative terminal, and another resistance going into the negative terminal, and with the second terminal or the positive terminal grounded. If we hooked up a resistor, operational amplifier like this, it becomes an amplifier, but it's an inverting amplifier because the output is equal to the ratio of these two resistances, but is negated. It's a negative result. So that's what we call this an inverting amplifier. So in essence, what it does is that it amplifies the signal, but it also inverts the signal. Okay. If we, and we're going to do this in a minute, I'm going to hook up this device in a minute so you can see. The other thing that we can do with this type of devices is create other kinds of applications. And in this particular case, if I replace this feedback resistor by a capacitor, and I'll show you this circuit in a minute. If I replace it by a capacitor, okay, what it does is that it integrates the input. It becomes an integrator, okay? So again, even if you're not familiar with op-amps much yet, what I'm interested in is in showing you in multisim how this can be corroborated. That's the main idea, okay? So we're gonna show that when we connect a voltage operational amplifier this way, it becomes an inverting amplifier. It amplifies the signal, but it also negates the signal or inverts it. If I replace this resistance by a capacitor, then the output becomes the integral of the input. See? That's how you do this kind of operations. So we're going to go into multisim and then show you how some of this works, or how we can make it work. All right, so now I'm in multisim, and I'm going to do the circuit from scratch. So what I'm going to do is I'm going to select a device now, right? And I'm going to go into my devices here, and I'm going to select, there you go. Under here, I'm going to select my op-amp, right? So this is op-amp, an operational amplifier. And to start, I'm going to select an operational amplifier. And there's so many options here. I just want to show you one of the simple ones. Let's see. Let's do the virtual one first, right? So I want to select the virtual amplifier because it's the easiest one to hook up at this point, right? So I'm going to select that one, and I'm going to just leave it there. As you can see, it has the three terminal connections. This one here is virtual, so I don't need to provide power to it. It's not like the real thing. In the real world, I'm going to have to provide power to this device, but to show you the introduction, we're going to do it without power in the device, okay? So that means that all I need is to hook up my inputs, my resistors, and then look at the output. So I'm going to put in a DC source, and I'm going to make it, and of course I need a ground, and I'm going to ground it. Okay, and I'm going to need another ground here in a minute. So now I'm going to make this a 1 volt, right? A 1 volt battery. And I'm going to flip this. And the reason I'm going to flip it, I don't have to flip it, but it's just I want to connect the device like to look like this, right? Just so that I can follow the example I had on the PowerPoint. So as you can see, I have the positive terminal grounded, and the negative terminal, I have the resistors connected, right? That's why I flipped it. I don't have to, but I just want to make it look like the ones I have here. So I'm gonna ground, and I'm gonna move this a little bit out of the way. So I'm gonna ground the the positive input terminal, and I'm going to connect two resistors, and I'm going to make them simply 1 and 1. 1 and 1, and I'm going to hook up 1 here, okay? And move this out of the way, and I'm going to hook up 1 to the negative terminal, and the other one I'm going to connect between the input terminal, the negative terminal, and the output. Okay, and I want to see what happens when this runs, right? So according to the theory, what I will have is an inverting amplifier, which amplifies the signal. Well, in this case, it's not going to provide amplification because they're 2 1s. So 1 over 1 is going to give me 1. So let me make this one a 2. And let's see what happens. 2K. And for easiness, I'm going to hook up just a voltage probe here and look at the output. And that's it. I'm going to run it. And when you run it, you have what we predicted, right? We have a gain of 2 because it amplifies the signal. The input signal is 1. The output signal is 2, but it's minus 2. See? It's minus 2. So that means that if I put an input sinusoid or input sine wave, it's going to give me a cosine wave because it's going to invert it, right? It does the same thing with AC signal. Okay. Now, to show a little more how this is actually working, I can change this resistance, and I'm going to make it a variable resistor, and I'm going to keep it as 10 again. And now I have a variable resistance connected there, right? So you can see now that if and right now I selected at 50%, so it's 5 kilo ohms. So I should see a gain of 5 when I run this, right? As you can see, it's right there, 5, right? Because the input is 1, the output is 5, but it's negative 5. Of course, as I change this, if I make it, 7.5, I'll see 7.5 gain. If I make it 100%, I'll see a gain of 10. If I make it 2 volt, let's make it, try to make it 1. If I make it 1, 10% of 10 is 1 kilo ohm, so I have a gain of 1, see? So the circuit is doing what it's predicting to do, right? Is amplifying the signal, right? So I wanted to show you this with this kind of devices.